Okay, so hello everybody. Now today I thought I'd do something a bit different. What I'm going to do is I'm going to search for some complex systems. Okay, so I've actually already found one. I've presented one here. So here it is, running from the initial time step. It starts out like a cube, and we keep applying these rewrite rules shown at the top, and it grows into a highly complex network. Now what I'd like to do today is to show you a process which I've done a lot, sort of behind closed doors as it were, which is basically looking through lots and lots of these rules and trying to classify what kind of behavior they have. The difference is that today I'm going to do it live. Okay, there might be the occasional break in the camera rolling, but basically I'm going to record all the process of me looking at these systems, so that to give a kind of record of how one goes about actually searching through a space like this. Of course, this is just my style, and being a live program, no doubt you'll see many different kinds of errors, but the basic idea is that I'm going to look at lots of different kinds of rules which produce lots of different kinds of behavior, and then I'm going to talk about what kinds of things we're seeing and try and come up with some kind of empirical classification schemes. So basically we're sort of creating we're going to try and create a sort of cabinet of curiosities, or Wunderkammer, or whatever it is they say in German, of different network rewrite systems with complex behavior. And we're going to try and get a feel of what are the different kinds of species of network rewrite systems, if you like. Now, I might be going a bit too far to make all these biological analogies, but I think they're fairly apt. Each of these systems begins with a cube and follows some very simple rewrite rules, as shown at the top here. But just by changing the rewrite rules a little bit, we change the behavior a lot. And sometimes the behavior can be extremely complex. And many have argued it can be as complex as real organisms, in fact. So perhaps some of these systems can create things on par with real life as far as complexity goes. And so for this reason, I think what we really want is a classification scheme, but we don't have a classification scheme yet. This science of understanding complex systems is still in its infancy, still in its kind of pre-Linnaean days. So we have to resort to this kind of making a curiosity cabinet style approach. And that's what we're going to do today. We're going to have a look at lots of systems, and we're going to try and make a kind of empirical, qualitative, approximate kind of classification of the sort of behavior which we see. I'm not going to use anything except online software, okay? So if you go to this website here, wolframdemonstrations.com, and then if you search for complex networks from simple, that should be enough words. There we are. So this is a demonstration which I've written, which basically allows you to do what I've been talking about. It allows you to look at lots and lots of different rules. And so basically what you need to do this project is a software browser. I use Google Chrome. You have to install the CDF reader, which is just a free plugin. So if you go to this website and click, you'll be prompted to install it anyway. And then you just need some kind of some kind of documenting system like Microsoft Word or whatever. And the basic idea is very simple. We have all these different rules at the top here. Each of these rules defines a particular network growth system. So this is rule number 1,645,074, okay? And this is the rule starting from time step 0. We begin with a cube always. And we keep applying these rewrite rules shown above. So if we move time along, our network changes over time as the yellow node moves and the rewrite rules are applied. And so if we run this system for a long time, we get a curious particular shape. And the thing is that these systems are extremely interesting and difficult to understand intrinsically. So the standard kind of mathematical approach of trying to prove theorems about the entire class of systems isn't going to really get at what are the most interesting facets of these systems. Because the most interesting things about these systems are their ability to create surprising and interesting emergent behavior. And it's almost inevitable that we won't be able to predict that kind of thing. So instead, we're forced into actually just looking at what happens. And so this is where it becomes very, very challenging and very, very interesting, because as people, we just have to look at these things and try to make some sense of it all. I mean, this particular program allows us to view these networks in different ways. For example, we can have a look at the 3D version of it. You can all do this yourselves through the browser, by the way. And we can look at different. We can look at these networks in different ways. And the point is to try and make some sense of it all. How can we classify them? So this is just one system, okay? If I go back to the rewrite rules, these are the rewrite rules at the top. Now I'll change the rule number, something over here, say. This creates a completely different system, something much more simple, okay? In this case, we're just seeing a circle being grown out. So it would perhaps be quite easy to think of what kind of class this system falls in. But this is our basic problem, is to try and classify what these different systems do. So I'll just show you a few examples. Okay, let's wind time on a bit. So you can see there's a wide variety of different behavior. Some of these things create circular networks. Some of them create very small networks. A lot of them create circular networks, in fact. Some of them create linear networks. Some create fractal networks. And once in a while, maybe once in every 50 rules or something, you find one which creates highly complex structures. So, I don't know, but I'm hoping one's going to pop up. This looks like a promising example. Yes, so here's an example of something which is more complicated. Okay, so basically what I'd like to do today is to go through some of these systems, and we shall just look at them and try and classify them. That's all we're going to try and do. We're just going to try and make sense of this vast array of different objects. And it's a very challenging thing to do. I mean, I think a good analogy would be to imagine that, let's say you just landed on an alien planet or something, and you find a load of strange alien artifacts scattered around the landscape. How do you classify them? This is the basic problem we're faced with. It's a very similar problem to the one which biologists are faced with, given all the organisms on Earth. So we're just going to try and see what kinds of behavior these rules have. So it looks like this one's producing a kind of circular structure. So if let's evolve it right back from the cube. So at the beginning it looks kind of interesting, but after a while you see that the way that the writer's moving is sort of repeating, and we're really getting a circular structure being produced. So in comparison to what's possible with these systems, this is fairly boring. So this is producing a circular structure. We can have a look at it in 3D as well, just to get a bit more perspective. So okay then, this is our first rule. So we'll use this snippet tool here. Excuse me. We'll use this snippet tool, which is a great thing to take copies of stuff. And so we'll take a copy of what we've just got and we'll paste it in our document. Okay. This is our first rule. What can we say about it? Well, let's just keep it simple. It's circular. Now, what else? Well, another thing that's important about these systems is that they can have applications, okay? So I'm quite into 3D printing, and so I can see that we could actually use this to make something like a necklace, okay? If we replace these straight edges with cylinders, we could use this to make a necklace. So that could be a potential application of these systems. So we might as well write that down as well. Okay then, so this is our first rule we found. Now let's just pick another system at random. So here we are. What's happening here? Well, this is what's going on time step 40. So let's look at what's happening further on. Okay, something fairly interesting. Right, so let's watch the evolution of this system from early on. What's happening? Now, I think these are the kind of cases where you're really in the same kind of situation as like a biologist trying to understand a mouse. I mean, a mouse is just too complicated to understand in completion. You can only say certain things about it. And I think it's pretty similar with a lot of these systems. So what can we say about this? Well, there is a trouble with these systems, and that is that Mathematica lays out the network in a particular way, but of course this network could be laid out in many different ways. So in a way we're much more interested in the way the structure's connected together than we are in the way that it's been rendered. Although actually the way Mathematica does render things is usually quite instructive. So let's have a look at this plot. Well, okay, for a start, let's take a picture of it because it's obviously a fairly interesting rule. So we'll use our snippet tool again. And we can keep a record of it. But what can we say about it? Well, let's have a look at it in 3D. I mean, I've never seen this system before, so I don't really know what to say about it. Well, for one thing, does it get more complicated? Well, let's have a look at what the system looks like. This is on time step 85. So this is on time step 632, and it's not really looking that much more complicated. So I'm going to say that this is I'm just going to write some words down which don't really mean too much. I'm going to say that it's cubical because the shape kind of reminds me of a cube, and that it seems to have a lot of parallel lines, and it probably has some kind of fractal aspect, and reasonably simple. It doesn't seem like there's been a lot of pseudo-randomness generated here. So, I mean, I'm only looking at this briefly. Of course, one could sit down and do mathematical analysis and statistical analysis for ages on a system like this and try and figure out a lot more about it, but that's not the objective of this exercise. We're just trying to get a very fast idea of a lot of things. So let's go on to the next system, something at random. Okay, another circular one. Right, so that's number 3. I'll just skip that because it's similar to something we've already seen. Number 4, linear. Okay, something new. Let's take a picture of it. So it's linear, kind of repeating pattern. Potential applications, let me think. Well, again, I guess it could be applied to jewelry and things like that, but I'm not going to bother writing that down. I think it's fairly easy to make linear network structures like this, so it's silly to write down an application for it. So let's pick another rule. Okay, this one looks like it's fixed, so let's just check. Okay, so it looks like it's stuck in a periodic orbit. So 1, 2, 3, 4. If it's a period 4 rule, okay, it's repeating every 4 updates. So again, let's take a picture. It lasts longer. There we go. And so this is period 4. And so a little diagram of how this thing works would probably be something like this. It does a few updates, and then it ends up in some kind of period 4 orbit. Okay, on to the next one. Another random rule. Okay, this looks like another loop, slightly more intricate, but nevertheless just something that's growing something like a circle. So we can ignore it. On to the next. Aha! Finally, something that's a bit more interesting. Right, so let's take a picture of this. So looks like we've finally happened upon something with a bit more jazz to it. So let's have a look at this system running from the beginning. Okay, it looks like the way the writer's moving is highly complex. It seems to be producing some of these kind of ladder structures, but there appears to be a lot of heterogeneity in the network itself. It seems like much much like a growing organism has an eye which has one kind of structure and a leg which has a different kind of structure, it seems as if the network which this thing's spinning out has very different looks in different places. So it has heterogeneous parts, complex writer movement. So let's make a note of this. Heterogeneous parts, complex writer movement. And of course, the great thing about this technique is that we have the number of the rule here. So if we want to know more about it, we can always come back and study it in much more detail using this app, or in fact, these pictures here really tell us everything we need to know. If you read the paper about these systems, I shall put a link to it. You can study this system for years since you know the rules. It's all deterministic. Anyway, so this is what's going on for the beginning. What about what happens after a lot of time steps? Well, let's have a look. First, let's have a look at a 3D version of this. Okay, so it seems to have a lot of ladder-like structure and heterogeneity, but this is just on a very early time step, so let's wind it on a bit. Okay, that's good news. It seems like it's persisting to be complicated, even after running for a long time, which isn't something you always see. Okay, so let's go really crazy now. Hopefully my computer can keep up if I run it for over 1,000 time steps. Great. So we're still getting something highly complex. I guess we might as well take another picture of this. Okay. So it seems like it's persisting in its complex behavior for a long time. What else can we say about it? Does it have any kind of fractal structure to it? It doesn't appear to have too much. You can't see many repeating patterns in here. Unfortunately, I think the web version of this doesn't have a zoom feature. There's a zoom feature in Mathematica, but I wanted to show you this kind of work being done purely online so that anyone could repeat it. Anyway, let's just run this thing for longer. Let's give Chrome a real challenge. Let's run it for 3,542 steps. Hoping that it doesn't crash. Oh wow, okay, we're still there. Right, so what is going on here? Well, it doesn't seem as if there's any specific fractal structure which has been followed. It's difficult to pick out particular repeating sections in it. It also doesn't seem as if, on a large scale, the system is particularly heterogeneous. I would say this is a little more like sort of cracks in stone, if you like. I mean, if you look at a stone, there's cracks everywhere. The cracks are complicated everywhere, but they're complicated in a similar way everywhere. So perhaps my original idea about this having heterogeneous parts is wrong. Okay, so let's look at something else. Again, I don't know actually, let's see. Run this system further, what's happening? Okay, it's growing somehow. Let's evolve it further. Okay, again it looks like we're the fact that I can put it on time step 12,057 and still see a fairly small network obviously means it's run into some kind of fixed point early on. So we'll set the time step low and look at another random rule. Okay, what's going on here? Seems that we've found another kind of fractal network. So what can we say about this? It looks pretty similar to one of the things we've seen before. Let's have a look at it in... Well, okay, let's take a copy of it for a start. Add it to our Wunder camera. Now, let's have a look at it in 3D. Well, yes, to be honest, it seems to be of a very similar ilk to one of the systems we've already encountered. This is on about time step 600. Let's have a look at the system run for a bit longer. Okay, so again, I'd say this is intricate, maybe fractal. I don't think it's too complex though, really. I bet someone could probably work out how this system works if they studied it for long enough. And it also seems to have a lot of parallel links, but I think that's just a symptom of the way that Mathematicus plotted it. Okay, so we'll wind the time back down and look at something else. Another circular rule. Another circular rule. Is that another one like we've just seen? No, this looks more interesting actually. Okay, so let's take a picture of this. Again, we can add it to our collection. Okay then, so what can we say about this? Well, let's have a look at it in 3D. It looks remarkably similar to the last one, but it definitely does seem to have some kind of fractal component to it. You can see the sort of repeating patterns in it. Well, okay, I think this is just similar to the last thing we encountered, so I'm not going to even bother saying anything about it. Let's just carry on our search. We'll go back to coloured and go back to looking at random rules. That's a small growing one, another small one. Aha! This looks a little more interesting. So let's run it for a bit longer. Is it yet another one of these parallel things? Ah, it is. Okay, well, we'll skip it. We've seen plenty of things like that before. I mean, if one's doing this, you know, and one has coding knowledge, one can put things into the system to filter out particular rules. I mean, you can easily filter out these rules that only grow to a very small size, or filter out the rules that always make circular. Aha! Bingo! Looks like we've just found something really nice and complicated. So I'm not going to waste any time. I'm going to grab that one. Let's pin this butterfly to the wall. paste. Okay, right then. What can we say about it? Well, this is only on time step 384. We'll have a look at it in 3D, and we'll have a look at it for longer. So it seems to be growing at quite a rate. It seems to be producing a very interesting structure with ladders and all sorts, and lots and lots of different faces of different sizes. And it seems to be naturally producing something like a non-orientable network. I bet this thing isn't planar. I bet it can't be drawn in the plane without having edges crossing over each other. Let's evolve it for longer. Let's see what it starts to look like. Okay, it doesn't seem to be taking on any particularly ordered features yet. So I mean, this might really be a... Well, I mean, Stephen Wolfram classifies cellular automata into 4 classes. The ones that go to fixed points, we've seen analogues of those. The small growers classifies periodic points. We've seen also small growers that go periodic. He classifies fractal patterns. We've seen those. Chaotic and complex. See, I think this would be a complex system as opposed to chaotic. It doesn't seem as if pseudo randomness has just been generated everywhere, like static on a TV screen. It looks more like it's differentiating itself and creating a complex structure. But perhaps that's an illusion. Let's run this thing for longer and see what it looks like. Time step 2235. Still, it looks very, very complicated. Interesting. So what can we say about this? Well, complex behavior. Heterogeneous parts. Some self-similarity. It's kind of like the Mandelbrot set. It's not like, I mean, there's self-similarity in the Sierpinski triangle, but that's really dull self-similarity. But in the Mandelbrot set, there's self-similarity, but it's also highly complicated. This is more like the Mandelbrot set. Now, there's a very interesting question here, which is, what is the very, very long-term behavior of these systems? So, if we just go back, look at the system in colour. I mean, how is this system actually being produced? Well, it's just a yellow ball called a writer, which moves around following particular rules, growing on extra parts of the structure and moving according to deterministic rules. Now, we see that for the first few thousand time steps, the system spins out a highly complex network. Here it is on time step 1500, and here it is on time step 2500 if Chrome will abide. And okay, it's still highly complicated. Doesn't look like it's going to suddenly change direction. But what you do see in these systems quite often is that after you've run them for a massive number of time steps, like maybe 100,000 time steps, then their behavior suddenly changes and they start producing repeating structures, and basically they go from complex to dull. Kind of like the way when you drop a seed in the ground, it sort of complicates itself and sends out roots and things, and then eventually ends up producing a serially repeating pattern. So maybe that's all this is doing. Maybe this complexification is just an early stage in the system's development, and later on it's going to end up going periodic. Or maybe it just produces a complex pattern like this which goes on forever. It's very hard to tell without simply running the system. Okay, so certainly up to time step 3320, things are looking pretty complicated. Okay, so let's just have a look at a couple more rules with different behavior, because I'm running out of time. I have other things I have to do. So, okay, this is a new kind of system. Seems to produce a more complicated circular structure. Now I imagine, yes, if we wind time on, yes, if we wind time on long enough, it looks like a fairly dull structure. But on a small time step, it looks like a more interesting kind of circular structure. So let's take a record of this using our snippet tool. Okay then, so now we can carry on. Whoops, that's the wrong slider. I want to change the rule. So I'll set the time low and have a look at some more random rules. Okay, this is obviously one which gets stuck at a fixed or periodic point fairly early in its growth. That's another circular rule. Circular, 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 a fixed, circular. Aha! Fractal. Okay. Maybe this can be our last rule of the day. So let's use a snippet tool again to grab it. Make sure we get the rule number in there, and let's paste it in our document. What can we say about this? Well, it seems fractal and fairly simple, I'd say. So if we actually observe the behavior in more detail and just wind it on, what's actually happening? You can see this yellow writer moving. It appears as if the writer is actually going in circles. Looks to me like it is. Looks like it's going round and round the outside. And it looks like we've got some kind of serially repeating pattern going on. So perhaps if we look at this on a large time step, we can see more of the fractal pattern. Yes, I think this is fairly evident. So maybe if I use the snippet tool, I can demonstrate it a bit better. So for example, if we zoom in on this particular part, okay, so it looks as if this entire sort of structure here is like a kind of big version of this structure here, which is like a kind of big version of this structure here, and so on and so forth. We seem to have some self-similarity in this. It seems to be a real fractal structure that's been created. So anyway, I'm going to stop there for now. I know for a fact that there are some other very interesting varieties of, let's call them species of network rewrite rules in here. In particular, ones that produce hyperbolic networks. Now, I'd like to encourage you to basically do similar things. There's loads of programs on here. I shall give a list in the comments of not just this network rewrite rules system. There's lots and lots of things on Wolfram demonstrations which are like my program here, which basically allow you to go in and explore the dynamics of millions of systems based on simple rules with the potential for highly complex behavior. And this is really a boundary point in human understanding. I know that sounds dramatic, but it's really true. Nobody understands how these systems work. In fact, most people think in principle it's impossible to formulate a general theory of how these systems work. So this is a program which allows us to explore cellular automata. Again, it's on Wolfram Demonstration's website. Again, it doesn't require any technical skills. And one can have a look at the behavior of loads and loads and loads of these very, very simple rules, starting from simple initial conditions. And again, one can create these kind of curiosity cabinets. The hope eventually is to get towards something more Linnaean, to actually think about classification schemes for these things. Why? Okay, I guess that's a question some people might ask. I personally, I think it's fun is a good enough reason, but I think another reason is that there will surely be some amazing technological applications for some of these very simple programs, but it's going to be enormously difficult for us to find the right programs for the right tasks. By inventing. I mean, who could have foreseen that such simple rules can create such complex patterns? Not me. I don't think many people could. So to actually invent something like this would be very, very difficult. But if we get a kind of qualitative understanding of how different spaces of programs, what kind of computations they can do, we can get a qualitative understanding of that by classification, exploration, etc. And if we do that, then we can find our technologies and our applications, and we can find systems which can be used to model things in a very succinct way.